Good day and welcome to this Saturday's technical session of the John Chappell Natural Philosophy Society. Today is the 8th of November 2025. I'm Ian Cowan, and today we are very happy to be able to announce that we have a speaker whom we haven't heard from before. He's published quite a number of papers which were drawn to our attention actually some time ago. They were published in the archive, the ARXIV system. And I had a quick look at some of them. They cover a panoply of areas, very, very interesting. And so I took the liberty of contacting the writer, who's Jorma Jormakka. He's actually, I believe it's the Finnish language. Jorma is actually based in Poland at present, and he very kindly acceded to our request to give us a talk on this particular paper, which is concerned with the refutation of relativity experiments, because we're all inundated with the statements, I'm sure, that you are wasting your time questioning modern theories of relativity because they've all been proved thousands of times by experiments. So Jorma's summary basically said that when pointing out very serious mathematical errors in the relativity theory, not simple slips of the pen, people try to argue that the theory has been verified by a large number of physical experiments, and therefore it must be correct, and therefore one is wasting one's time to challenge it. Now, the presented paper, and this is, by the way, the paper that appeared in Vixtra, the Vixtra, yeah, not ARXIV. So I should maybe point that out. I think most of you, particularly in the United States, will know this, that this is the Cornell University archive, but it does require to be passed by a number of referees, most of whom will probably be quite orthodox and will be very reluctant to pass papers which are questioning orthodoxy. So this Vixtra, which is just ARXIV backwards, is a bit more of an open system. I haven't actually used it myself, but a lot of people who have presented very interesting philosophical and mathematical and physical theories have presented on Vixtra, and obviously Jorma has used Vixtra. So the paper was printed in Vixtra, and what he's doing, he's presenting that today. I think he's actually going to present it through a video, pre-recorded video. The paper looks at some of the most commonly presented experiments that claim to verify relativity theory and gives alternative explanations to the results of those experiments. So if he's right, that's quite serious. That most of the current ideas and validation, so-called validations of relativity theory, might actually be incorrect. So as normal, I'll bring Jorma up in a second, and I'll give an opportunity to say a few words about himself, perhaps since most of us don't know about him. And I have control of the video because we've already loaded it and it works, I'm happy to say. So Jorma will be able to tell me when to start the video, and then we can all go and have a cup of coffee and hopefully keep our ears pricked. And then at the end of the session, which will be maybe an hour or so, we'll have an opportunity to put the questions to Jorma, which will have been posted through the Facebook and YouTube. I don't think anybody's in yet. I'm a little surprised now, but then we'll have a number of people in the green room that we'll address. I see we have 2 people in already. I hope we have more. So yeah. So Jorma, you're up now, and what I'm going to do with your permission is I'm going to disappear now, which means I'll be in the background. If you need any assistance, just say Ian, and I'll come back. But I'll give you the floor entirely to yourself for as long as you want, for a moment or two. You might want to spend a minute just introducing it and saying a word about yourself, and then then just tell me to bring up the video. I'll bring it up, and then I'll maximize it, and I'll bring your photograph off, but you'll still be audible. As I always say, in fact, I discussed this with Jorma just 5 minutes ago, but I always say this, that we prefer not to interrupt the speaker or indeed interrupt the video. We'll let it run. But that's not an absolute commandment. If anybody has really urgent matter that he cannot wait and he doesn't understand it, we will interrupt. We will interrupt that. But that's an extremist. We'd prefer not to do that. So I'm going to give you the floor now, Jorma, and it's all yours now.
So hello. So a few words of myself. When I was working last time, I was professor of military technology in the National Defense University in Finland, Helsinki. And before that, full professor of telecommunications in Aalto University in Finland, Helsinki. And before that, full professor of data communication in Lappeenranta University, also in Finland. And I made a dissertation in mathematics long ago, and also made another university, electronic engineering, technical university, nowadays Aalto. And I studied theoretical physics once and even thought of making a dissertation on it, but then switched to mathematics, so I didn't do it. But I actually studied the topic long ago. So I will just not speak of what Ian Cowan said that I would speak of. It's not about that paper only, it's about the whole thing. Relativity theory in total is wrong. So let's hear the video. I'm not going to talk it another time, so let's just run it. Please. Good morning, my name is Jorma Jormakka. I will be talking about. Good morning, my name is Jorma Jormakka. I will be talking about if relativity theory is verified in any way by experiments or something else like theory. The case is that it is not verified. Let's take a simple case of the Lorentz transform and what's the error in Lorentz transform. Let's on Earth send from A1 to B1 in vacuum light. It will, the speed of light will be c. Let's think about another planet just like Earth, and there we also send light from A2 to B2, and again the speed of light is c. The clock in A1 and B1, they tick at the same time. Likewise, in the other Earth, the clock at A2 and B2, they tick at the same time. Now, consider that our Earth would be moving with a speed v with respect to the other planet. Then what does the Lorentz transform say should happen? Lorentz transform in this case says that yes, you will get if you measure from our Earth the speed of light in the other planet, you will get the speed of the light on the other planet as c. But only if you go on turning the clock in B1 backwards by the amount of v divided by square of speed of light times the distance from A1 to B1. So then you don't have synchronized clocks, and you are not going to measure the speed of light as c on the Earth, and you have to especially turn in the correct way for each planet that you are going to measure. So this is certainly a wrong way of measuring the speed of light. you can do this test as an imaginary test and just verify that the Lorentz transform is wrong. Why is it wrong? Is that the time in the moving inertial frame is a local time. You get this kind of a formula that the time depends on the place. It is exactly the same kind of formula that you would get with time zone time. So if you fly from Helsinki to Stockholm, the Swedish clock is 1 hour behind. The flight time is 1 hour. You leave at 9 a.m. You arrive at 9 a.m. But the flight time, how long the plane took, is not the difference between local times. And in the Lorentz transform in the moving frame, exactly what you calculate as the speed of light is a difference between the local times. That's why it is wrong. You have to take a projection. It's a local time coordinate system. If there are any experiments that prove this special relativity time dilatation and length change, no. About length change, nothing. About time dilatation, they give some experiments, like for instance a muon in a laboratory. A muon is an unstable particle. It lives longer, but this does not indicate that the speed is the cause for the muon to live longer. The muon is accelerated, and the cause is the acceleration time dilatation. This is true. The acceleration does cause time dilatation, but it is not because time changes, but because the time in the equations that give you the oscillation time, that is Schrödinger equation and Dirac equation. It is not a real time. It is a time that depends on the gravitation field or acceleration. There is a similar test with cosmic particles. They also live longer than they should be, but they are also accelerated. Then there is the Sagnac experiment, where time goes around in a circle, like sending from one satellite to another and going around the Earth. It actually refutes relativity theory, but in some way relativity people explained it. The explanation is wrong. Einstein also explained the twin paradox. There is no way to explain the twin paradox. It is a refutation of the special relativity. Einstein explained that the astronauts have to meet again in order to compare the times. This is not the case. The Lorentz transform. There is no need for the world paths to meet. Then mass, special relativity also says that mass changes. You can test this very easily. Put any kind of mass, like kilo of flour, on your table and see if it turns into a supernova. It doesn't. But it should if mass depends on the velocity, because there you can always find such a coordinate system with moving with a constant speed, with respect to which our Earth moves with the almost speed of light. Such mathematical coordinate system, just imagine such. And in that coordinate system, the mass of this 1 kilo of flour would grow huge if mass depends on velocity. And under its own gravity, it would turn into a supernova. But you think that it would happen only in that coordinate system? No, it would happen in every single coordinate system, because different coordinate systems, different inertia systems, are just different views to the same physical world. If the mass turns into supernova in one inertial system, one coordinate system, it does the same in every single coordinate system. So nothing happens, so special relativity fails this test. There is also a theoretical reason for this. The relativistic mass, or as they now say, relativistic kinetic energy, is not possible because it violates the conservation of energy. If you calculate in a case when a mass falls down, for instance, in a gravitational field, it has potential energy, it turns into kinetic energy. You have the potential energy as giving force F, space derivative of work or space derivative of potential energy. The kinetic energy also gives a work. It is time derivative of the partial derivative of the kinetic energy with respect to v, to the speed. You put this equal so that the work that the energy does is the same as energy, must be the same. The force must be the same and the work must be the same. And you will notice that the only possible kinetic energy formula is the Newtonian formula where mass does not change. Every other formula gives a violation of conservation of energy. Are there any experiments? No, there are no experiments at all verifying the relativistic kinetic energy. The early experiments made in the early 1900 by Kaufmann, Buchner and Lorentz, they found that there is apparent mass. They called it apparent mass and they found that it is different for transverse, that is when the force is orthogonal to the velocity, and longitudinal when the force is parallel to the velocity. Bertossi measured in the 60s with a particle accelerator, and that measurement is claimed to show that the relativistic kinetic energy formula is correct, but it does not show. I checked this measurement, it shows a longitudinal apparent mass. It does not match at all to the relativistic kinetic energy formula. How about nuclear power? Doesn't at least E equal mc2 prove something? Well, obviously this formula is correct because we have nuclear power and nuclear weapons. But Einstein's proof is wrong. It is based on the relativistic kinetic energy formula, which is wrong. So we don't have a valid proof at all for this famous formula E equal mc square. But that is not so difficult. We can make a simple proof just from energy F times S, and mass is and force is F is ma. Just divide those, you get the difference of energy divided difference of mass is acceleration times the difference in space distance, and you can divide it to maximum acceleration. What would be the speed that maximum acceleration reaches in a shortest time moment, and that is c. And what is the fastest speed? It is also c, so you get c square. So then you integrate and get this famous formula. So it is very simple formula. It doesn't at all require Einstein's proof. What about the fine mass, fine structure constant? I heard this so many times, this fine structure constant, and I finally looked at it. And of course, it is so that Dirac's equation, which is an improvement of Schrödinger's equation, is based on the relativistic mass, relativistic energy, kinetic energy formula. That is relativistic mass, and it gives a good correction term that gives rather well the fine structure of spectrum lines in an atom. But exactly the same correction you get from longitudinal apparent mass. So the longitudinal apparent mass does give the fine structure constant correction completely correctly, and it fits to the Bertos's measurement in 60s much better than the relativistic mass formula. How about the gravitation and acceleration and dilatation, time dilatation? Now there is such time dilatation. This is quite true, but it doesn't mean that the time actually slows down. It doesn't happen for all clocks. If we have a pendulum clock, it runs faster in higher gravity. If we have a sundial, it runs the same. If I have my old windable clock, it also almost certainly runs the same. But atomic clocks are influenced by gravitational fields. And you can get this correct gravitational time dilatation formula in general relativity. You get it from the Schwarzschild metric, but you can get it in a scalar gravitational theory from Newton's gravitational field, and it's the same formula. But the real reason for this is that Schrödinger and Dirac equations, they are heuristic equations. They are not derived from anything. They should be parameter there, like there is in the pendulum clock, that the gravitational field influences the oscillation time. There is no such, because these are heuristic formulas and they work in practice, but they are not derived from anything. The pendulum period has this G explicitly, and it is derived from Euler-Lagrange equations for energy of the mass in the pendulum. So these other ones, they are not derived from anything, and I think that in some complicated way gravitational field changes the local electromagnetic field which you have, because in atom nucleus there is positive charge and in the electron belt there is negative charge, so there is electromagnetic field in a very close distance, and how this reacts when, for instance, atoms get closer because of the gravitation. Something causes that atomic clocks slow down in higher gravitation field. Then there is this GPS clock advance. GPS clocks do advance, and they have to be corrected, and the correction that you can calculate from general relativity theory gives a correct, quite good correction. So isn't this a proof that relativity theory is correct? No, because you can get these corrections from other ways also, and they are incorrectly calculated in relativity theory. Firstly, the bigger part of this, the time dilatation on the Earth caused by gravitation, this is the same exact formula that general relativity theory calculates, derives from the Schwarzschild metric, comes from the scalar gravitation theory, from the Newtonian gravitational potential. So you don't need to use general relativity for that. Time dilatation by the velocity doesn't exist and cannot exist, and the twin paradox is absolute reason why it cannot be so. But there is another dilatation which is caused by the acceleration. The orbit of a satellite is not straight, it is round. There is the centrifugal force, and it causes acceleration dilatation. And if you calculate this acceleration dilatation, you get exactly the same correction as the correction from special relativity because of velocity. The relativistic calculation forgets this acceleration time dilatation, but it shouldn't, because certainly it should be there. If they include it, then the estimate goes wrong from relativity theory, but it goes correctly if you just notice that there is no special relativity theory time dilatation. Cannot be. A simple example where general relativity fails is that the Newtonian relativity theory works very well. So you drop stones, you look at the planets, everything works fine with Newtonian gravitation field. And the sad news is that the Newtonian gravitation field cannot be approximated by Einstein's equations, so general relativity cannot give any solution that is stationary field and spherically symmetric field. And we know that the gravitational field around the Earth and around the Sun are stationary and spherical. You may say that what about the Schwarzschild solution? It is not a valid solution because it's not a metric. The Schwarzschild solution is given above here in this slide, and if you convert this, it is in spherical coordinates on R3. Convert it to Cartesian coordinates of R3. You will see that it will have some cross terms. Then you can move it to local coordinates in a point. Let's take the point which is on the x-axis. And in the point you will get this formula which is here in the lowest level. It's a good Riemannian metric, only that it is not a Minkowski metric. It should be Minkowski metric part. So here should be BR, also here BR and BR, and it is not. So this is not good. It is not what it should be. It should be so that in general relativity the metric gives a Minkowski's metric on the tangent space. There is in Cartesian coordinates of RT only one form for a spherically symmetric time independent, that is stationary metric, and it is this form. And in the local coordinates it is similar form. And the metric that we get from Schwarzschild's solution is not of this form. The metric that we get from Schwarzschild constant speed of light. It is different speed of light in the radial direction and in the orthogonal direction to the radial direction. The metric has to be of the type mentioned there. And if you use spherical coordinates, the only possible way you can do is that you have PR in all of those components, dr square, r square, d theta square, and r square sin square theta d phi square. They all must have the same term, beta. But if you don't have them, then you get such cross terms like dx1 times dx2, dx2 times dx3, and so on. And those terms there should not be in a metric. And the metric additionally has to be a scalar metric if you want the speed of light to be constant. And it is even stated in general relativity that in the tangent space of each point the metric must be Minkowskian, else Schwarzschild solution does not have this. So general relativity is proven incorrect just by noticing that the gravitational field of the Earth is stationary and spherical. And the implications of it is that practically all of the experiments that are claimed to prove general relativity, they are wrong. So gravitational redshift does not prove it. It comes also from scalar gravitation theory, the same formula. Mercury's periodic precession is calculated from Schwarzschild solution. You can't do that. Black holes calculated from Schwarzschild solution. GPS clock advance calculated from Schwarzschild solution. Shapiro delay calculated incorrectly from Schwarzschild solution. Light bending also calculated from Schwarzschild solution. Let's look at it deeper in the next slide. In light bending, there is the geodesic Lagrangian way of calculating dynamic equations in general relativity. The Lagrangian that is used is the Lagrangian for test mass. It is incorrect Lagrangian for light. You cannot use it for light because light always uses such paths where the word path ds is 0. And this Lagrangian only varies over word paths where ds is not 0. Light does bend around the sun, but it bends because there is something around the sun. There is some matter. Light does not bend according to this geodesic metric. When you correctly calculate the geodesic metric for light, you will get light bending, but it bends incorrectly, in wrong way. Here are the two Lagrangians. So in this Lagrangian for test mass, you take a derivative of the proper time and calculate it. But this varies over the paths where ds can change. For light, you cannot do that. You have to keep ds as 0 all the time, and you have to make Lagrangian taking some coordinate like dr and taking another for picture. You can solve this Lagrangian perfectly well, and you get solve everything that happens, and you notice this very strange thing that in a gravitational field like Newtonian field or Schwarzschild metric gravitational field, a freely falling stone does not accelerate. It is not use this Lagrangian geodesic in normal way, this way. Indeed, solve also completely solved, but you cannot the amount of light integration parameter, and the integration parameter by anything, so possibly have predictions in anything. have known it.
I'm sorry, the sound is disimproving, Jorma. I don't know if it's just momentary. Are you experiencing some breakup in the sound of the video?
I'm not doing anything with the video. No.
Yeah, but when you hear it, as I do, I'm hearing it breaking up a lot.
No. In my side, it's not breaking. But what I saw was that there came the screen on top of it, and I couldn't see all the time the picture, the slides. Is in your case, is it the voice that is breaking?
In my case, it's the voice that's breaking, and I'm wondering, is it just my system?
Could it be the
Jim,
connection?
May I ask you, are you hearing the audio perfectly, or is it breaking up? Jim Keane.
Yes, I'm hearing it. Are you talking to me, Ian?
Yeah, I'm taking the liberty of just
Ian,
asking
are you
Jim.
talking to me?
Yeah, if I may, sorry, but it's just we're having some audio difficulties.
Well, I can. There's a little bit of transmission difficulty with the video, but I can see the slides well and hear Jorma speaking quite well, and so I would proceed with the video. I think it is effective.
Okay, thank you very much. Thank you, Jim. I just thought I'd check it, Jorma, but no, well, I'll get rid of myself and I proceed again.
Yeah, report by astronomers. For Schwarzschild metric, you cannot actually calculate at all. Now, in this slide, I explain why metric must be always a scalar metric that is induced by a scalar field, because light travels along word paths where ds is 0. When you set ds to 0 and then take light beam to direction of one coordinate axis, you will get the speed of light, and you can do it to all coordinate axes, and you notice that this A must be the same everywhere, and it can be expressed as a square of a scalar field. So only scalar metric is possible. It is conformal image. Scalar metric means that the field is in the Euclidean space, exactly like the electromagnetic fields are conformal. There are many more errors in this. Let's look at the Mercury perihelion. So Einstein calculated a correction to the precession of the perihelion of Mercury from the geodesic metric. This geodesic metric that does not even make a freely falling stone to accelerate. So from that metric. There is another calculation which uses the geodesic equation. I noticed it from the web, and there are 2 incorrect Christopher symbols in the calculation, so it is incorrect. I should have. Okay. So about the precession of Mercury's perihelion, old astronomers did manage to calculate this precession quite well. The formula has only a small error. It is necessary to calculate it with approximations because in Newtonian mechanics you cannot analytically solve a multi-body problem, and the effect of other planets, must be done with approximations. So there is an approximation error. It would be very strange if an approximation error caused by imprecise approximation, that would be perfectly matched by some other mechanism that was not even considered, like the relativistic slowing down of something. So how could it match? That would be a surprise. So how did Einstein know this? Einstein knew this amount, the error. He had read the astronomical reports, he knew the error, so he tuned his calculation to give this error. And it is now claimed, or Einstein claimed so, that you cannot calculate from Newtonian mechanics any better than the old approximation. You certainly can. If you add more detail to this calculation, I calculated a better approximation, and the effect of Jupiter explains most of the approximation error. Einstein then used his fake calculation with the geodesic metric to discard the scalar gravitational theory, Nordström's theory. So he applied his fake metric into Nordström's theory and got the wrong result, of course. But Nordström's theory is also not correct, because it is still a geometric theory, but the physical world is not a four-dimensional space-time. It is a three-dimensional world, in fact a flat world with movement, with change. You can prove it, that it is three-dimensional. It comes from this, that only three-dimensional flat space where the ball is area of ball is growing as 4p r square allows expressing spherical mass as a point mass. And we know that this approximation is extremely good because it's used in planets' orbits, and it lasts very long time. They have made those observations of planets for quite long time, so we know that the sphere of a ball in our world grows as air to square. It means that the space is flat, Euclidean flat space. How about the graviton then? Now somebody got a Nobel from finding a graviton that is a spin 2 graviton. There cannot be this spin 2 graviton because as the Schwarzschild solution is incorrect, there is no other Einstein equation that could correspond to the Newtonian gravity, and therefore Einsteinian equations are wrong, and therefore you cannot use them, and therefore you don't have any basis for this spin 2 graviton at all. It's not a tensor equation, it is a scalar equation. You can only have a scalar gravitational theory. But there is another reason why I don't quite understand how somebody could have found a graviton, because you shouldn't. Fields like light or gravitation is not so that there are gravitons or photons going around in this field. They are fields, they are not particles. They interact with matter occasionally as particles. When they interact with a quantum system, like an atom, atom will either take a photon or take nothing. It makes a state transition, it's a state machine, so it accepts only quantized inputs. In order to see a graviton, you would have to have a quantum system of gravitation. I don't think there are any quantum systems of gravitation around, because what would it be? Gravitation is a very weak force, so in an atom gravitons cannot cause electrons to move from one orbit to another. Gravitation does keep the planets together, but certainly it would be a too huge graviton to move a planet to another orbit. And even so, the orbits, well, there is some quantization in the orbits. We know that there are preferred orbits, but they are not so quantized like in an atom. So where did this particle idea come from? It came from Einstein's paper from which he got the Nobel Prize, the photoelectric light. There he explained that the light has this particle wave dualism, but it does not. Massive particles seem to have this, but light does not. If we imagine, like in the Copenhagen interpretation of the two-slit problem, that light is in photons. So a photon chooses either one way or two ways in the two-slit experiment, and then you make an observation, and it turns out that your observation influenced the decision that the photon made earlier. So time is reversed. This is of course not possible. This problem disappears if you, it only comes because you think about photon as a particle. It's a field, and field takes both ways. You disturb one way, so only the other way continues. So where can we measure a graviton? I don't think we can measure a graviton anywhere now. We could measure it inside a black hole or close to a black hole, or we can measure it theoretically in models of the Big Bang. Maybe there could be a gravitation quantum system. I said that there are no black holes, but I mean that there are no black holes of the general relativity theory. That is the Schwarzschild solution type black holes. There are cosmic black holes. They are black. They look black. There are photographs of them. They are dense material. So the problem of finding a graviton is that you first would have to find a quantum system that works with the gravitational force. Light can interact with matter in a non-quantized way, like in Compton scattering. So light is not composed of photons. Energy can be moved in any units, not in certain quantums. And you also have this same with the gravitational field. Gravitational energy in any units. We don't need to find the gravitons. We see these kind of gravitational waves, like for instance moon causes the tides. That's a very slow gravitational wave. But we don't see gravitons. There are more problems in relativity theory. For instance, I have to go back. People claim that many equations like the Dirac equation or Maxwell equations are Lorentz invariant. They are not. Even the Einstein equations are not Lorentz invariant. About the black hole, yes, there are cosmological black holes, but they are not general relativity black holes. Now, if you want to have more information of these, I have several papers, grouped them into different groups. I wrote over 20 papers. So I'm Jorma Jormakka, and in 15 minutes we'll show that general relativity is totally wrong. I only need to show that the Schwarzschild metric is not a valid metric, because the Schwarzschild metric is the only solution to the Einstein equations that in some sense approximates the gravitation field that we have around the Earth and the Sun. The metric is shown there, and the spatial part of this metric should then be Riemannian metric in 3 dimensions. It will be shown here that this is not a Riemannian metric and that it cannot be written in local Cartesian coordinates. Riemannian metric is defined in local coordinates. In each point there is the tangent space, and in the tangent space there is the inner product. And using the inner product you find an orthonormal basis and can make a metric. If we think about this Schwarzschild metric, it looks like that you would get to the tangent space a quite valid Riemannian metric. So think about a point there and take the coordinate axis that is to the same direction as the radius. Then orthogonal to it are the angles, and you have a plane there, can pick up a y coordinate and z coordinate orthogonal to each other, and you have local Cartesian coordinates in the tangent space, and it looks like that the metric gets this form. But it happens to be that this is not exactly so. It only looks like that. This form would be a valid Riemannian metric, but the reason why this is not what Schwarzschild metric gives is that in Schwarzschild metric the radius r can point to all kind of directions, not only to the direction that we have here for the x1 coordinate axis. It fooled me for many years. I also thought that this is indeed a valid metric in the tangent space. I mean, the metric is valid, only that Schwarzschild metric doesn't give it. I earlier used only such weaker arguments to reject the Schwarzschild metric. It doesn't have the constant speed of light, and in the tangent space it is not a Minkowski metric. But the strong argument is that it is not a metric at all. Let's write coordinates of R3. So we can move from these Cartesian global coordinates into a local Cartesian coordinates by just a shift. So that is easy. But here we have the problem. So we first divide the metric into 2 parts. The second part is very clearly just dx to square plus dy to square plus dz to square. And then we have left the part with the dr to square. How to transform that one to Cartesian coordinates? There are actually 2 formulas for it. One is the more limited form that is here. You don't use this for radius. You would use this for a fixed vector, like Cartesian coordinate vector. Then you would do exactly like this. So if you have a vector, you can differentiate the vector and take the norm of it, and you would have this kind of a formula. This is not what you should do, but let's see if we would transfer in this way. So here we are trying to transfer in this way, and what do we get? We get exactly flat space. Space multiplied by BR. This is not Schwarzschild metric. It is the space part of a Minkowski metric. So we have to go to the other formula, which is a more general form of the previous formula. So you start from this that R2 square is the sum of squares, and you differentiate this formula. And this is exactly the formula that gives you the famous formula how to convert dx2 plus dy2 plus dz2 into dr2 plus r square d theta 2 and plus r square sin square theta d phi 2. So that is the correct formula. So here we have the correct formula. Let's insert it there. We get something looking very bad, because there will come these cross terms dx and times dy, dx times dz, dy times dz. Now that is not good. We shouldn't have those in metric. Those orthogonal coordinates, Cartesian coordinates, they are orthogonal, and in orthogonal coordinates you cannot have those cross terms. These terms should disappear. They should disappear from the terms that are in the d theta and d phi, but they don't disappear now. We can see what would happen if we assume correctly that the Cartesian coordinates, global coordinates of R3 are orthogonal also in Schwarzschild metric. This is true. Then we would just select some nice point where all of those x square, y square and z square give the same value, and we have less to worry about, so we can reduce this metric into more simple form, and then we set only one differential non-zero and the other two to zero, and get in coordinate axis what's the value of this metric. So in x coordinate axis it will be like that, in y coordinate axis like that, and in z coordinate axis like that. Let's sound. And because a metric in orthogonal coordinates can only have diagonal components, we would have the metric as like this, and then can transfer it to spherical coordinates, and it is again not a Schwarzschild metric. So it looks like the Schwarzschild metric would claim orthogonal Cartesian coordinates are not orthogonal. Because with orthogonal coordinates you certainly have to have only the diagonal elements. That's what orthogonality of the coordinates means. But we get these cross terms, dx, dy, dx, dz, dy, dz terms. So there are only two possibilities. Either the Cartesian coordinates are not orthogonal, or Schwarzschild metric is incorrect. It will be the latter one. We can find such a point, another point, on the x-axis, where certainly the Cartesian coordinates are orthogonal. So then certainly here we have this kind of a metric on the axis only. And we convert this metric back into spherical coordinates. So the spherical coordinates are differentiated, and then the differentials are squared, and we have here the result. We see that there are now cross terms dr, d theta, dr, d phi, d theta. Spherical coordinates have these cross terms always if we don't have b is 1 in the metric. This would indicate that the spherical coordinates in a Schwarzschild metric are not orthogonal, but they are certainly orthogonal. So what is the problem here? So we had The metric is described in spherical coordinates of R3, and as it is in spherical coordinates of R3, we can convert them to Cartesian coordinates of R3 with the usual formulas. Then we set R to be parallel to the x-axis, and we have certainly orthogonal Cartesian coordinates. But when we convert the result back to the spherical coordinates, it's not a Schwarzschild metric, and it is indeed not metric for orthogonal coordinates at all. It has those cross terms. So what is going on here? What is going on here is that you cannot define metrics in global spherical coordinates of R3. You have to define them in local coordinates. I make here a comment of which formula you can use of those two formulas for dr2. So the first one you would use if you have fixed coordinate vectors like in Cartesian coordinates, and then the vector direction doesn't change, and then you use the simple formula, but with r, the direction of r can change, you have to use the more general formula. So there are only these two formulas, it is correctly calculated. The verdict is that you don't have a valid metric. Schwarzschild metric is not valid. You cannot define this kind of a metric in global spherical coordinates of R3. It does not give a metric in local coordinates of the time space. So it's not valid. Yes, surely you can make such a function, but it is not a metric. A metric has to be a real metric in local coordinates, because that is what the Riemann metric tensor requires. So Riemann metric tensor is used for deriving the Ricci tensor, which is needed in the Einstein equations. So in order to have Einstein equations, you have to have a Riemannian metric. And the Riemannian metric is defined in the tangent-space of each point by there being an inner product, and the inner product produces for you local coordinates. You take these local coordinates normally as Cartesian local coordinates. Of course, as local spherical coordinates, but that is extremely difficult to work with, so you take them as Cartesian local coordinates. And then they are orthonormal, and the metric in local coordinates must be diagonal. And if you want to define a metric in global coordinates of R3, global spherical coordinates of R3, first of all, a 3 manifold doesn't normally embed to R3, but if it does, like in this case, then you still don't have the freedom to define your metric in global spherical coordinates of R3 in the way you want, because it has to be a metric in the local coordinates. Einstein thought that he can, and Schwarzschild thought that he can, but this is not the case. You can have a diagonal metric in global spherical coordinates only if the metric is a scalar metric. It has to be just like in the slide, in the bottom there is the formula, it has to be like that if you want a diagonal metric. If you want some more general metric, then your metric definition in the spherical coordinates of R3 cannot be diagonal. You will have the cross terms in that metric. So the requirement for the metric is that you have to have in order for it to be diagonal, it has to be a scalar metric. In general relativity, it's even worse. The time part of this metric, pseudo-Riemannian metric, pseudo-Riemannian metric that is used for space-time, it has to have the time part also with having the same function, because otherwise you do not get locally constant speed of light, and you do not get Minkowski space in the tangent space as the metric. So it has to be a scalar metric. Local coordinates, metric in local coordinates that claims that the Cartesian local coordinates are not orthogonal, but they are orthogonal. So a Riemannian metric is always defined in local coordinates, not in global coordinates. Do not define them in global coordinates if you want anything more than a scalar metric. But there is no other than scalar metric. If you want the speed of light to be constant, it has to be scalar metric. There are no solutions to Einstein equations with a scalar metric that are spherical. This means that Einstein equations do not approximate the Newtonian gravitation field, or the gravitation field that we know that there is around the Earth and the Sun. It means that relativity theory is false. And didn't really publish anything. You may ask, if this is so, that everything is wrong in the relativity theory, how can it be? It's 100 years old theory. Now that's a good answer, a good question, and there is a simple answer. There is a gang. I can demonstrate it. I just sent 10 papers, different papers, 10 of those that I showed before. They all show fatal errors in the relativity theory. And I chose a top journal because if you send to an average level journal, they treat it like a hot potato, they will not review it. So you would expect that the top journal would feel that they would have to respond in some way in order not to be a fake journal. If the field is shown fake, then the top journal of the field is also a fake journal. Now, the outcome was very much what I expected it to be, that they are rejected by the editor and not reviewed, so no comment on the content at all. Because they cannot show errors. There are no errors, these are real problems. And why did I do this experiment? Why did I write those 20 papers? Not really in order to improve theoretical physics, it is a very bad field. And not because it's my hobby, no. I made this because I wanted to show an example of a taken over field. So, relativity theory is a taken over field. Taken over fields, taken over method is based on old principles, several hundred years old principles of pillars. So every system is standing on pillars. Take the pillars off or destroy them, and then the system collapses. There is more to this theory, of course, but this was the theory, the way how in 1700, 1800 social systems were changed. You can do it also in any field, like science, but you have to do it from inside, so infiltrate the system. And in science, there is, for instance, this pillar, or actually the most important pillar is that arguments are evaluated correctly. Now, this is not the case now. You can give any arguments against relativity theory and you won't get any comments from anybody criticize anything. Your papers will be rejected without reading. And in this way, and this is the only way how false theory can stay accepted for 100 years and may stay accepted still another 100 years. And for sure Einstein knew that. Seems to be getting broke. Yeah, okay. Okay, it seems to have been broke.
Is that the end of the video, Jorma?
Okay.
Have I correctly stopped it? I think it ended
Okay,
there.
that's it then. Seems to be that video stopped, and in any case there was only the farewell. You should fix the theory.
Okay. Well, thank you so much for that exposition, which fitted very well into the time allotted. I know we wasted a bit of time in the middle with some problems, which didn't seem to be too serious because people said, oh, there were minor problems. But yes, I found this quite fascinating. And of course, I omitted to mention that these things are recorded in real time and will be available as soon as we finish the speech presently. It'll be available on YouTube, on the John Chappell Natural Society YouTube channel. So maybe just a couple of comments and maybe a question, if I may, for Jorma, and then we'll go to the general questions. I think there are only one or two actually that we need to address, and then maybe we might have a brief discussion. Yes, well, your last point actually is well taken. You know, these pillars, sort of they seem unassailable, but if you do break them down, well, everything on top falls. And yes, that's a good point as well. From inside, I think to a certain extent within the society we do meet that requirement. We have a lot of people who are not professional scientists and so on, but we have a lot of people with a lot of conventional degrees and so on. So the mainstream, which frequently would dismiss, say, the John Chappell Natural Philosophy Society as a whole load of crackpots who don't understand relative theory, it would be very hard to maintain. So, yeah, I think that there's so much information there. It's quite fascinating. Maybe I could just ask one question just before we go into the general points. Yeah, all these points about the Schwarzschild metric being an invalid metric and so on, and you're taking the foundation from general relativity, which is quite interesting. Could I just ask, when you looked at these two things, which are ostensible confirmations of the theory, the light bending close to the sun, and the difference in the observed value of the perihelion shift of Mercury and the theoretical value. With regard to the light, I'm just wondering, would you accept, see, the Newtonian value of that is actually half what Einstein comes up with in terms of the general theory of relativity. So I'm just asking, would you accept that you talked about mass around the sun being responsible for some of that?
Yeah.
So would you accept the Newtonian value of half, taking light to be influenced by gravity in the same way as particulate matter would?
I don't know this question. What I was thinking that light bends in any medium, and there is something around the sun. There are ions there. It is not empty space. Light has to bend on this medium, I think it's just normal bending of light in any medium other than a vacuum. One would, of course, have to know what there is, and I have no knowledge of what there is, and I don't think that most people have any idea of what there is. So I spoke with somebody who claimed that there are a lot of particle-antiparticle pairs there. Who knows?
Okay.
So
Because
there is.
Many people would agree very much with the thesis that you presented with regard to this point, but some people, like the late Dr. Edward Dowdy, said there's no influence on light deflection. It's all occurring within the corona of the sun. Whereas some others, like myself, for example, I accept the Newtonian calculation, but it would give half the value of the Einsteinian one. The other point I just want to raise...
But the Einsteinian calculation is wrong. I mean that I tried to make the Einsteinian calculation. It's not possible to make. If you correctly calculate it, you do not get any value for the bending. It is all in the integration parameters. The calculation is wrong.
And presumably you're saying the same about the other thing, about the perihelion shift of Mercury.
Yes.
In fact, you were suggesting that maybe it was almost fixed, dare I say, because Einstein knew this value of 43 seconds of arc or something.
Yes, I know. Einstein knew it. Einstein knew it, and Einstein also knew how much light bends. He could not possibly calculate correctly from his theory how much light would bend in around sun, and he could not possibly calculate correctly from such a geodesic Lagrangian that doesn't make even a mass accelerate when it falls down. It is nonsense. It's nonsense.
There was an earlier derivation by a German by the name of Gerber, who basically got the same formula by looking at the finite speed of transmission of gravity. But some people say that Einstein may have plagiarized that to a certain extent. But anyway, obviously that they're both incorrect in your terms. Well, okay, we might come back to some of those points. Thank you very much. There are a couple of questions on the social media, so let's try to dispose of those first. I think people are quite intrigued by what you're saying, and probably they're all almost speechless. We don't have many questions, but I hope we'll have some further discussion, because we've had some comments in the private chat, which actually you have access to, Jorma, as well.
Yes, I see, but I'm just trying to find questions.
About how don't worry about that. Don't worry about that. I'll highlight the questions in a second. But
yeah.
If there are about 3 questions, I think, on the social media, and if I just try to address them, I think one is by Professor Hallam Bhutia, but another is by Jim Morrison. There have been other comments made which are all very valuable, but they're not specific questions. Yeah, let me see. He's made a number of comments, but okay, here we are. Just while I'm getting this up. Yeah, so the question from Professor Bhutia is: you show that Bertozzi, that Bertozzi experiment matches the longitudinal mass formula, not with gamma m. Yeah, presumably it doesn't match with the gamma, but can it be derived without Lorentz transformation?
Now I have the paper in Vixra. You will, and also in ResearchGate. And there is a table 3. It's the calculation of the longitudinal mass in Bertozzi experiment. About like that is the name. And there is the table 3. And I calculated, and somebody else in Vixtra even plotted this calculated values into a graph, and it shows very clearly that the relativistic mass formula does not match Bertozzi's results, especially in high velocities. I did not understand the ending of this argument. What was the argument that one should?
I don't know. I think he might be saying, well, if you accept that, and you accept the result of the experiment, can it be derived without using Lorentz transformation? Which I suppose your thesis would be that the Lorentz transformation is
whose transformation?
Lorentz.
Yes, absolutely. Without Lorentz transformation, you get the Lorentz transformation or very similar transformation to Lorentz transformation just from geometry. I have it in this paper that you put as at the title of this talk, which can be found from Vixra. There is the calculation that I will explain what this calculation means. Think about push starting a car. In the old times, you must have been push starting a car sometimes, pushing it to start. And you notice that when you are pushing it, it starts to accelerate very well. But when your running speed equals the car speed, it does not anymore accelerate at all. And then you wonder, did the car's mass grow to infinity, that you cannot accelerate it anymore? No, the moving mass does not feel the force from the field which tries to accelerate it. And when you calculate, take some kind of a interaction model for this, how the field interacts with the mass, you will get actually geometric formula which is Lorentz transform, just from this kind of very simple calculation. It's not the Lorentz transform derived as Einstein did, but it gives you the same kind of a transform, and this transform has this difference that you will get a different mass for the mass if you push it from the parallel direction or from orthogonal direction. Exactly like Lorentz and Kaufman found out that there is transverse mass and longitudinal mass. Yes, you do get this Lorentz transform formula, but it is not Lorentz transform, actually.
Okay. I was going to bring in Jim, had two questions, but I see he's joined the green room, so we'll get him in there. I think he wants to ask about your views about the Michelson-Morley experiment. And I think he wants to ask you, as a retired professor, could you not publish in AR XIV? But we'll get him to talk directly to you on that. So I have 4, 5. So would anybody, I'll ask you to come in, but would anybody wish to come in at this stage? If he raises his hand, I'll bring him in immediately. Dennis P. Allen Jr.'s camera is off. I wonder, Denny, if you could put your camera on. Jim, are you ready? There are 2 Jims. Okay. Well, I'll bring Jim Morrison in with those 2 questions. You wanted to talk about the MMX, and you wanted to ask Jorma, could he not publish an ARXIV as a retired professor? Is that so, Jim?
Yeah. Hi. Hello. Nice to meet you. Yeah, I noticed on your profile that you are a retired professor.
Yeah.
Have you ever tried to publish an ARXIV? Is that now a problem?
Have I ever tried to publish these theoretical physics papers? Well, I just sent 10 papers to a journal, and they were all rejected by editor.
Yeah, but I thought that as long as you have a formal academic credential, that you can publish anything.
No. No. No,
well,
you cannot.
Right?
Once upon a time, there was such a time, but this time is not anymore. You have now blacklists, forbidden topics, such like that.
Wow.
So try.
In that they may say, well, you're a traitor, so we're going to blacklist you.
you get to be blacklisted very easily if you try to publish anything that is against mainstream. You will be blacklisted. I'm already blacklisted so much that I cannot get my papers to archive anymore. Archive moderators remove them immediately. I even got blacklisted in Vixra when I tried to publish a paper. Yeah, that is an achievement. Yes, I know. That is an achievement. When I sent these 10 papers to a journal, it was a Springer Nature journal, General Relativity and Gravitation. And I collected these 10 rejections from editors. And I put the beginning, a very brief and short and complete proof that general relativity is wrong to the paper, and then listed those 10 rejections. And I tried to put it to Vixra, so Vixra moderators did not publish it. It is only in ResearchGate now, but you can see it there. So that is the situation. You cannot.
May I ask, just for curiosity, Jorma, have you been investigating this in a dissident way for many years? Or did you
5 years.
Recently come to
5 years?
Okay, it's not very long, actually. It's not very long.
No, it's not very long. It is 40 years ago that I studied theoretical physics, or 45 years ago. But then I moved to other fields. I was supposed to make a dissertation at that time in about quantum Gauge field theories. But I moved to mathematics and then to telecommunication. But I did study that field, so already at that time I did know that the relativity theory is wrong, but I didn't know how much wrong it is. That is, it was obvious that the twin paradox is not answered by Einstein.
Well, I might say, if I may, that thinking people would come to that conclusion. I mean, when I was first taught relativity, I did think there was something amiss with it, but I couldn't quite put my finger on it. It's really over the years. It came to me not 5 years ago, but maybe 30 years ago. I've been at this for maybe 30 years ago. Oh, okay. Well, thank you very much. Anything else, Jim, before we move on? Thank you for raising the point. Yeah. What's your brief view, Jorma, about the Michelson-Morley experiment? Because Jim has been proposing that we, if I may speak for you, Jim, that we try to perform an MMX experiment in outer space, away from the Earth's influence, to see what directions we go.
MME experiment is incorrect. It was incorrectly made. If you make this experiment, you cannot possibly get anything but a null result, because you are splitting light which has the same frequency into two paths. When these paths join, they will have to be in the same phase. You will not get any interference. It is impossible. I wrote a paper where the error is. So that experiment is faulty in general. You cannot do it like that. But if we talk more generally about this, so light, in my opinion, has constant speed in the rest frame, but it does not have constant speed if you are measuring it from another inertial frame. So if we measure light correctly, not like an MME experiment, we should get constant speed of light to all directions in vacuum. But it is only most probably the gravitational field that causes this effect, or some other field, maybe electromagnetic field. You will have to, around some large mass point, you will have the speed of light constant to each direction. But whether to do it in the space, In the space, let's
Another
see.
way, yeah, go on.
If you do it in a space, then you have vacuum in the local space everywhere. In my opinion, you should get a constant speed of light in the space measured locally. If you try to measure it from another inertial system which is moving fast, you would measure that the speed of light is not constant.
Yeah, my position has been that it was only null because it was too small for the instrument to detect that there is a relative velocity to the Earth rotating within the ECI, which is much smaller than what the instruments were designed to detect.
But the question is, in what substance, what is the one where the light is undulating? I mean, the light is wave. It has to undulate in something. So,
yes.
So I would guess that it undulates in some kind of a field, like gravitational field or electromagnetic field, and that's why that's what gives the rest frame, and there it is constant. But
and that
Do you conceive of an
reference
ether?
frame is the Earth's inertial frame.
Ether. Ether, yes. But what would that ether be? So I don't know if there is need for ether if we have a field.
But that is the ether.
Yeah, I mean, field can be an ether. Field works like an ether,
Yeah.
And for that reason, if you are close to a large mass like the Earth, your field is stationary in this mass.
Stationary. That's the ECI.
Yeah.
The Earth's inertial reference frame.
Or ether drag.
Rotates within
They're all
that.
different ways of explaining maybe the same concept. Yeah.
Okay.
Okay. I think we better move on because there may be one or two other people we want to bring in. So you can come back if you wish. Thanks very much, Jim. We'll just see what the situation is because all I have to do is get your photograph here and bring it down. Okay. Now we have actually James Keane and I think Danny's trying to get in, and we also have Harry here. Jim, yeah, I was just about to, as you put up your hand, because you've made a number of points here, and perhaps you'd like to put them directly to Jorma. Thank you, Jim.
Well, first, great talk, Jorma. I liked it. I really think you're on the right track, sir. You might be interested in empirical evidence supporting your position that I've published, for example, 2 papers of empirical data which relativity as a viable theory. I had a few questions here which our viewing audience of this video might be interested in knowing. What is acceleration delay? Can you clarify that?
I couldn't hear. What is
acceleration delay?
Okay, acceleration. Yeah. Okay. Acceleration dilatation is a concept that comes from Einstein's partially incorrect idea that acceleration and gravitation cannot be distinguished. They can slightly be distinguished. One gives twice as high dilatation, but both give a dilatation. Now, the geometric explanation for why this should be so, this I do not have. You can try to think of some geometric reason for it, but I do not have. But yes, acceleration does give dilatation, and gravitation also gives dilatation for the time. We know this from Bound-Repka experiment for gravitation, and we know it from the analogy of gravitation and acceleration both act in a similar way. That yes, I don't have explanation. What?
So may I just ask, I think it might help, is acceleration required? So in other words, if you have an atomic clock which is moving in a straight line, will that not also experience a time retardation? I don't use the term time dilation.
No.
You said no. Yeah, I thought you were saying
I say no. If it moves, if it moves with a constant speed, it will not experience any time change. It cannot, because otherwise you can make the twin paradox, and the twin paradox is impossible to solve. You must have the same time, but there is this aspect that there is no time. There is only change. So time is our artifact that we created, and we can create this artifact, and it works in such a way that if something moves with a constant speed, doesn't have any forces affecting it, the time can be taken as the same.
We had some very nice chimes, I think, coming from your background when the hour was coming out, when you were talking about time, which was relevant. But those would be very interesting experiments to do to see if that is so. I mean, for my part, I think the problem with the twin paradox is the reciprocity which has been imposed upon them by this relativistic theory. If you have an atomic clock which, say, is moving linearly and does lose time, well, then that's it. It's an absolute effect in comparison with the clock, which is in the inertial frame, or is in the ether frame, if you like, of the ECI.
Yes, it could be. It's not excluded that
some experiments, maybe.
Yeah, it's not excluded. I don't exclude this possibility that linear motion, time in linear motion would be different. This would come from the ether theory. If you would have a global ether, then global rest frame. But if you don't have global rest frame.
Take the Sagnac experiment, which I'm not sure if you mentioned, but here you have an effect which is dependent. But people would say up till quite recently that it had to be a non-inertial table which was actually rotating. But experiments have been done by Rudyong Wang, which shows that it's a linear effect actually as well. You get the Sagnac effect.
Yes, I don't think that the Sagnac effect is influenced by it being round. You can make it with satellites so that they are very, very straight, those lines, and whatever dilatation there comes, it is not affected by the roundness. But I don't see
anything else. Okay, well that's interesting. It's left open there. And anything else, Jim, before we maybe bring one or two other people in?
Yeah. Jorma, what are non-quantized interactions?
Like Compton interaction, like Compton scattering. In Compton scattering, light moves slightly electrons. You can have this, for instance, it can move on just as well a space shift. You have the radiation pressure. So that is not quantized.
Okay.
It can come in any amount of energy.
Okay. I would consider any amount of energy. Exactly.
Any amount of energy.
In other words, those would be approximations. Those would be expressions or equations which are approximations, or which could be approximations of what is in fact quantized at a more microscopic level. Okay, another.
Okay, it could be, but it is at the moment, at least, it's thought that it is in Compton scattering. Any amount of energy can be transferred. It's not in quantums of any kind, but it might turn out to be wrong. But I understand that it is possible. And this is my argument why
Point well taken.
one should not think of light being photons. It's photons only when it interacts with the quantum system.
Okay, well, this is a question of discreteness versus.
With regard to light bending, you might be interested that in my work, the actual energy density of the vacuum is actually greater than of particulate matter at STP or standard temperature and pressure. In other words, this supports your idea about light bending. You mentioned particulate matter around, say, the sun, and I presented data showing that actually there's in what physicists call the virtual sea of particles, as it were. There's actually more energy there, which would also contribute to the light bending, and also support your thesis that general relativity is wrong. Last question, and this is a very general one, is why do a Lorentz transform at all in the first place? In other words, if you have the velocity vector required to do a Lorentz transform, why do you need to do that at all?
Boy, to do. No, I don't think that they should. Could you? I have difficulties in hearing because this connection is breaking in some way. I couldn't get the question.
Would you like to repeat it, James, or shall I say? I'm a bit louder.
The velocity vector. You can't hear me?
I think he's saying. I think I'm a bit louder. Am I, Jorma?
Yeah.
If the velocity vector do a Lorentz transform, why do you need to do one at all in the first place?
I don't want a Lorentz transform at all. I think it is a totally wrong transform. A Lorentz transform naturally comes, for instance, in Maxwell equations. It is Maxwell equations have invariance over Lorentz transform, but I consider it as many invariances. They do not mean anything. I do not need Lorentz transform, but in the case of apparent mass, we have the Lorentz transform. It has been measured. It was measured by Lorentz and Kaufman and Buchanan. So that is correct, and it must be derived from something, and I derive it from simple geometry. Simple geometry that if you have a field pushing some mass, you will get there the Euclidean triangle. And Lorentz transform actually is nothing else except for Euclidean triangle. One angle straight and two other angles.
Pythagorean system, basically.
Yeah.
Okay. Could we maybe move on now, Jim? Unless you have anything very, very quick, because we're running out of time as usual. So thank you very much, Jim. Thank you. Thank you. Okay. Now let's see where we are. Now, gentlemen, I mentioned. I don't think we have any ladies today, but I mentioned that your papers had been referred to the CNPS, and that got me to contact you. But actually, the man who first brought this to my attention was Harry Ricker, who suggested that you might be an appropriate speaker today. And I see Harry is here, so even though he hasn't put up his hand, Harry, I'm going to add you to the stage. And would you like to put anything directly to Jorma, because you're the man who first drew him to my attention?
Yes, I do have a couple of comments. One is thank you for your presentation. I think that the general relativity part and your disproof of the Schwarzschild metric is actually more important than the other part, quite frankly. And the reason that you came to my attention was I was looking for people who didn't believe in general relativity. And you came up and Stephen Crothers came up. Are you familiar with Stephen Crothers?
No.
Okay. Well, I'm just kind of would suggest maybe you might want to look at some of what he's doing.
I can write his name if you can spell it.
Crothers. Isn't that it, Harry?
I think so. Crothers, Stephen Crothers. Now he's got a number of videos. He's got videos on YouTube. So he's published papers where he disputes the validity. He doesn't believe in black holes, and that sounds like you don't believe in black holes.
No, I believe in those photos which show objects that are black. So there are these kind of objects there are.
Please, let's not argue about that. Black holes are something that astronomers claim exist. They claim they exist at the centers of galaxies.
I don't believe in those. I don't believe in those.
Believe in those. Okay.
No, right. I believe in this. I believe in this that there can be a neutron star. Throws out a nova or supernova and becomes a neutron star, and then it doesn't have any energy that it can anymore emit. So it will look black, and it cannot emit even though it has fermions, because there is a fermion conservation law. So when it has emitted,
we're not talking about that as black holes. We're talking about. I'm talking about black holes that you see
they don't exist.
An astronomy book, and they tell you all about black holes. They're at the centers of galaxies. They've discovered.
No. They cannot exist.
And they're all based on the Schwarzschild metric. Yep. And you're saying that's wrong. Stephen Crothers doesn't believe in that. That's how he apparently, when he studied at in university in Australia, he became dissatisfied with general relativity and the equations that they were using. And so I think there's a similarity. Now, I do know of other people who disbelieve in general relativity, but you seem to be more of a mathematically oriented. You seem to have mathematical proofs, which I think is kind of interesting. Other people do have proofs, but they're not that many. That's kind of the key point. You're a very small group of people.
Yes, well, I don't know how these false theories can exist. There's another false theory. It is the quantum field theory, Richard Feynman's stuff. It's also completely wrong. I haven't written yet, but I have studied this already quite a long time. I don't know how it happens that these fields get taken over, and then false things are being kept alive. But it is like that.
Okay, well, I thank you for taking your time to give us this presentation. I think we're a minority of disbelievers in the existing dogma, and so I appreciate your talking to us today.
No, thank you.
Well, thank you.
Okay,
George Bernard Shaw said the majority is always wrong, so we need to have no concern about that. And thank you for drawing my attention to Jorma, Harry. It's been quite fruitful, and now we have a recording for all time. So thank you again. Okay, now Dennis Allen, I don't know if he's come back. Dennis, can you hear us? No. Okay. He doesn't seem to do. I was hoping to bring him in. He's asking. Okay, so the microphone seems to be. Yeah. Okay. Let me see. Anybody else just before we finish off? Okay. So see what this thing says here. Yeah, I just had one or two things which maybe I didn't have time to go into. Let's see. Well, actually, the acceleration thing has been brought up already, and the gravitational effects and so on. Just something we've been discussing. It's come out of some of my equations. I've been working on maybe analogs between, say, electromagnetic energy transmission and fluid dynamics. And James Keen, whom we were talking to earlier, working with his own theories of binary mechanics, we've both come to maybe a similar conclusion, I think, maybe from quite different angles, that perhaps when you're looking at the proportionality between the total energy of a system and mc squared, well, maybe E is proportional to mc squared, and the proportionality constant might not be 1. It might be something like E equals k mc squared. You see, some of the experiments, such as the first artificial transmutation by Cockcroft and Walton in 1932, claimed to prove that equation experimentally, E equals mc squared. But what it actually proved is that E is of the order of mc squared. So, for example, E could be something like 3/4 mc squared, which I think was similar to an equation which was developed by Hassenhurl maybe in the 19th century. I don't know if you have any views on that at all, Jorma, or you've looked into it at all.
No, I have not looked at it. No, we don't have any proof that E equal mc square, because Einstein's proof is wrong. So any kind of there are many possibilities. That proof is certainly wrong. So then one can make a proof like I wrote, but that is in a discrete model. Maybe the model is maybe it's not discrete, so maybe we cannot calculate like that. I'm quite open that it might be something else.
Okay, so you have an open mind on that.
Yeah,
okay,
yeah.
No, okay. Thank you very much. So before we summarize and finish off, anybody else like to come back? If you want to be a moment or two, if you want to raise your hand. No. Okay, I think. Right. Well, what I normally do is, well, I invoke the situation whereby we'll have a recording immediately on YouTube, and I think it will benefit us all, including myself, to go back and look at that at our leisure, and perhaps if we have any further points we want to raise, discuss them, or indeed put them to you, Jorma, if that's possible. So within the 2-hour period, it's hard to think of everything. Things will occur to you later. So what I'm going to do, if this is agreeable with you, is I'm going to give you the entire floor again for as long as you want. You could have a minute or 2 or 3 or 4 minutes if you want, just to summarize what you did today. And maybe in the light of the questions which came in, maybe and insofar as they were addressed, maybe just give us a bit of a pointer as to how we might go further and what might be useful to think about later. And when you finish doing that, I'll come back and officially close the meeting. So is that all right? So I'm going to disappear and give you the entire floor now for as long as you want.
Well, I just made a not to have the floor, but okay. But this, what one can say about this relativity theory is that it is wrong. But the most important thing is not that relativity theory is wrong, but that very many fields were taken over and are taken over. And I don't know why it has happened, but it is completely true. And it's not only this one. I could have made a similar talk about quantum field theory and many other topics which are not connected at all with physics. So something is very much wrong. That's all I wanted.
Well, thank you so much. I'm almost tempted to quote Hamlet, the Prince of Denmark, something is rotten in the state of Denmark. But you talked very eloquently about these pillars. And I think we're all helping to chip at the base of these pillars. And certainly from the point of view of the society, you're a very valued addition to our thinking and our whole skepticism about what is accepted, basically without any analysis nowadays. It's become political, and it's become, the darling of the media. So they come up and they say, "Oh, anybody who questions that is a crank, and you're a denier, and it's all been approved," and so on. And you've addressed these experiments indeed. And then you've dealt, as Harry said, you've dealt analytically with the situation, which is actually very useful. I'm an analytical man myself, but a lot of us are more quantitative. They might find it a bit hard to understand. Stephen Crothers, whom Harry referred to, by the way, is analytical as well. So you'd probably find that it would be of value to get in touch with him and maybe compare your analyses. And by the way, with regard to the quantum work you've done on the quantum mechanics and so on, we'd have you maybe think about that, and maybe in next year, in the new year, give us a presentation on how you've analysed that to be wrong as well, because we're quite impressed with the amount of work that you've put into the burden of work in making it clear to us. You've made a very clear video, and I'm sorry, there was only a tiny bit of audio breakup in the middle. It wasn't too serious, but it was very, very valuable for us. And I think, as I say, it's a record for people who are analytical, people who are more practical, and for people who are philosophical even. I think it's been very, very useful what you've done, and thank you so much for giving us a very clear exposition. I'm always amazed, in a language which isn't your mother tongue, no doubt, but it's excellent. So unfortunately, the time has caught up with us again, and I do have to stop the recording now, which I shall do in a moment. But I'd like to thank everybody in the Facebook and in the YouTube for having participated, and even where some of you have been just making comments between each other about contemporary science and Three Eye Atlas, Comet, and all that sort of thing. You're very welcome. Thank you so much for coming today. And of course, everybody in the green room. I'm sorry Dennis Allen couldn't come in. There's some probably problem there, but thank you very much for participating and giving us the benefit of your discussion. And last, but of course not least, to our speaker, Jorma, for having agreed quite without any delay to my invitation to give this talk, and for having actually he had the system up very well, because we always have a rehearsal maybe for about 20 minutes before every meeting starts for a speaker who hasn't spoken before, and sometimes it's a bit tortuous. We have to go through trial and error, but actually the system was up when I came in. The video was up, so all I had to do was press a button, and everything worked very, very clearly. And so thank you, Jorma. We hope to see you again. We hope maybe you'll join some of our Saturday presentations now that you know the link is, and I hope you'll consider my invitation to come back to us on a subject of your choosing. It may be a further expansion of relativistic phenomena and analysis, or it may be giving a similar analysis, first analysis to quantum theory and how you perceive that to be erroneous. We'd very much welcome that. So without further ado, I'm going to end the recording now, and I wish you all, wherever you are in the world, probably most of you are in the North American continent, I think. We have our friend here. Yeah, well, he was in Mexico as well, from the North American continent, and in Europe, a few of us from Europe. I wish you a very good day.